let me start with some notation. So our K will always be an algebraically closed field. The characteristic is P. In general, it can be positive. We usually denote by Tn an n-dimensional torus. So you take a multiplicative group of your field to the power of n. So if you want to think in the special linear group, just take the subgroup of diagonal matrices. That's maximal torus of dimension n minus 1. And
maybe you come closer and try again, because it worked just a moment ago.
Try again.
Try again.
That's strange.
Just come a bit closer and try again. Usual thing. We did it a minute ago. I don't know. I'm sorry.
Now I caught up.
okay. I
Okay.
think this is
Yeah, so it's not in focus, right?
Get that.
okay. Then we use UN to denote an n-dimensional unipotent group. So for example, in SLN, if you take the triangular matrices where diagonal is identically 1, that is a unipotent subgroup that has dimension n times n minus 1 over 2. What else? We need the Borel subgroups, so we denote this by B. So this in general is a maximal close connected solvable group containing a maximal torus. Again, it's useful to think in the special linear group if you just take all the subgroup of upper triangular matrices. So this time we include the maximal torus. And we've done parabolic subgroups. So here we can think of them as close connected subgroups containing a Borel subgroup, but we're going to use them in very often with a geometric definition as stabilizers of certain subspaces. So here in SLN, if you take any subspace in the natural module, you take the stabilizer, you get a maximal parabolic, or you can stabilize a whole flag, and you get other parabolics. Okay, then I'm going to need something about rational modules. So I'm going to give a quick setup of highest weight rational modules. So we start with any irreducible rational KG module for a simple algebraic group G, and you take a Borel subgroup B, then there exists a non-zero vector in the vector space, such as B fixes the one space spanned by V. And you get an associated character, given that B contains the maximal torus, and this character is called the highest weight, and your vector B is a highest weight vector. Turns out that this is the unique one space fixed by your Borel, and essentially this highest weight completely determines the module, in the sense that irreducible rational modules are going to be parameterized by these highest weights, and they are going to be, two modules are going to be isomorphic if and only if they have the same highest weight. Okay, so for a quick example, so again, if we take SLN, and we assume that the characteristic P does not divide N, so that we can take the Lie algebra of trace 0 n by n matrices as an irreducible module. Here you can think of the action as conjugation by SLN. And here I'm giving a highest weight as, hey, it's epsilon 1 minus epsilon n. What I mean by this is that if you fix, this is with respect to the maximal torus of diagonal matrices, so this is going to pick up the first and the inverse of the last entry. And the highest weight vector, if you are in the Lie algebra of trace 0 n by n matrices, is going to be a matrix with zeros everywhere and a 1 in position 1n. So this is just an example. Okay, so with this setup, I'm ready to describe the motivating problem. What do we do? We fix G. This is going to be our big group. It's a simple connected algebraic group over our algebraically closed field K. And then what we want to do is we want to have H and J be close connected subgroups of G. So they're always going to be close connected. I'm not going to write that further on. And we define a set of double cosets, which you might have seen before. So this is the definition, just a generalization concept of a coset involving two subgroups. So this partitions the group G. And we ask a simple question. When is a set of double coset finite? Okay, so it's a simple question, and of course there are some situations where the answer is trivial or well known. So for example, if H and J are parabolic subgroups, so it could be a minimal parabolic like a Borel, by the Breuer decomposition, you know that you always have finitely many double cosets. So in particular, for example, an upper bound for the number of double cosets is going to be given by the size of the Weyl group. In some situations, there's only one double coset. So what happens if you have one double coset? It means that you can factorize your group G as a product of H and J. So it means that you can write every element of G as a product of something in H that is something in J. So for example, the group SO7, you can write it as a factorization as a product of a group of type G2 and a P1 parabolic, so stabilizer of a singular one space. Or for example, SO8 as a group of type B3. So here B3 is the Dingin diagram, and a P1 parabolic, where B3 is an irreducible subgroup of SO8 via the spin representation. Okay, but the good thing overall here is that these situations where we have factorization are understood. So they were classified already in '96. And it turns out that this is a very important situation, because there's a result by Brandon that says that if H and J are both maximal reductive and we have finitely many double cosets, then there's only one double coset, which means that we are in the previous case of a factorization. Okay, so let's think about this. So if they're both maximal reductive, we don't need to worry about the situation because it's equivalent to understanding factorizations. If they're not reductive, they are contained in a parabolic. So let's say if we assume they're maximal, we are in the first case if both of them are parabolics. So we don't need to worry about that. So the critical setup is when one of them, here we say J, is a parabolic, again assuming they're maximal, and the other one is reductive. So this is going to be the setup that we're going to be considering. So J is going to be a parabolic, H is going to be a reductive subgroup. We're going to take H to be just simple. Okay, so in this setting, the problem has already been solved when the big group G is of type A, so think of SLN. So Guralnik, Liebig, Macpherson, and Zeitz in '97. How did they tackle this problem? So, as mentioned before, J as a maximal parabolic is just a stabilizer of some m-dimensional subspace in the natural module. And so, since J is a stabilizer of some subspace, understanding when there are finitely many HJ double cosets is the same as understanding when does H have finitely many orbits on PMV, which is the variety of m-dimensional subspaces of V. Okay? And this is precisely what they do. They find all irreducible modules for semi-simple algebraic groups with finitely many orbits on varieties of subspaces. So in particular situation when M is 1, so that we're looking at orbits on one spaces, we like to give this a name, we call these finite orbit modules. So before I give you their result, their classification, let me give you a construction where finite orbit modules are easily found. So these come from internal modules, and I'm going to give you a quick construction. So here you have gamma, a simple algebraic group, and you have a parabolic, which you want to write in a Levy decomposition as the product of the unipotent radical Q and H, which is a Levy subgroup of your P. And then you take an H invariant composition series for Q, so you start from Q0 being the identity, and then all the way up to Q. And what happens is that each quotient, Qi plus 1 of Qi, has a structure of a rational irreducible KH module. So this is a nice way to take parabolics, take the Levy, and find some nice irreducible modules for the Levy. And the important thing is that there's a theorem, Richardson, completed by Alvarez, that says that the Levy subgroup has always finitely many orbits on each of these modules. So there are finite orbit modules. In particular, if we take the derived subgroup of H, we get a semi-simple group that is going to have finitely many orbits on one spaces. And the good thing is that we have a list of internal modules. So what do we see here? This is going to be the notation I'm sort of going to use in tables. So the groups are given by their Dynkin diagram. So for example, in the first line, we see the classical groups. The module is given by its highest weight. So for example, lambda 1 corresponds to the natural module for the classical groups. And then in the third column here, since we have this construction for eternal modules, I'm giving the simple groups gamma, from which we can find a parabolic where this construction is possible. So for example, well, we all know that for the classical groups, we always have finitely many orbits on one spaces, but there are some other interesting examples. For example, E7 here, so that's the minimal module for E7 that has highest width lambda 7. This tells you for free that E7 has finitely many orbits on one spaces of its minimal module. And what's also interesting are these semi-simple but not simple examples. So here, let's take AN D5, and the notation lambda 1 tensor lambda 4 means that we're taking a tensor product of the natural module, the lambda 1 for AN, with the lambda 4 for D5, that's a half spin module. So overall you get a module which is, well, if we're taking, for example, A1 D5, it's a 2-dimensional tensor, a 16-dimensional module, that's 32-dimensional module. And why is it interesting? Because this also tells you that D5 has, for example, finitely many orbits on two spaces because of this A1. And if you take A2, it also tells you that D5 has finitely many orbits on three spaces. Okay, so given these internal modules, I can state their first result. So you have H, your simple algebraic group, V, your irreducible finite orbit H module. Again, this means that H has finitely many orbits on one spaces. Then either V is an internal module, we've seen this is a nice construction, always giving you finite orbit modules, or the pair HV is one of the following. So this is the type of result you're going to see all over. So you get some nice classifications. We have an infinite family at the top when the characteristic P is not 0. So this is, okay, let me just describe the very first line. So you have a group of type AN, and the module here is going to be a tensor product, for example, the first one, of the natural module with a twist of the natural module. So that has dimension m plus 1 squared. And so they show that, I mean, for AN to have finitely many orbits on one spaces, the dense orbit needs to have finite stabilizer. Why is that? The dimension of AN, think of that as SLN plus 1, is n plus 1 squared minus 1. and that's also the dimension of the variety of one spaces. In general, take the dimension of V, subtract 1, that's the dimension of the variety of one spaces. So a dense orbit needs to have stabilizer, which is finite. So that's the only occurrence of this phenomenon, where a stabilizer of dense orbit is finite. Okay. Now, they also classify the cases where we have finitely many orbits on K spaces, but this time K is bigger than 1. So same setup. Assume that H has finitely many orbits on the variety of K spaces for K greater or equal to 2. So then either V is a natural module for H. Again, we know already that in that case we have finitely many orbits. Or the triple HVK is one of the following. So again, finite table of possibility. We see some interesting things. For example, some of these were coming from the internal module. So for example, we see this D5 that I was talking about. So D5 on the half spin module has finitely many orbits on 2 spaces and 3 spaces. And probably this is a good moment to mention that the highest weights here are all given up to field and graph automorphisms. So I'm only giving the lambda 5 because we can get the lambda 4 by graph automorphism. Okay, so I've described what was sort of known about this problem. So let me tell you my setting. So we consider the same problem, but as it's been solved for the special linear group, we go further and consider the upper classical groups. So our big G is going to be either a special orthogonal group or a symplectic group. So as Donna described, in the first case we are stabilizing a symmetric bilinear form with some extra conditions if the characteristic P is 2. And in the second case we are stabilizing an alternating, a non-degenerate alternating. So what do we need to do here? Our J, our maximal parabolic, okay, we saw how you can index it by some subset of the nodes of the linked diagram. So here pk denotes when you just delete one of the nodes, so that's a maximal parabolic. Also think of this as a stabilizer of a totally singular subspace. So a subspace where the form is identically 0. And our H is, as before, a simple subgroup of G acting irreducibly on V. So what are we trying to achieve here? To classify the triples, where we have finitely many double cosets, we are hunting for irreducible H modules with some properties. So we want the module to be self-dual. This guarantees that H does embed in either SOV or SPV. And, well, we want H to be acting with finitely many orbits on the variety of totally singular subspaces. Here I denoted by adding a TS on top. Okay, again, because J is going to be the stabilizer of some totally singular subspace. Okay, so we start with a nice reduction. So same setup, H is a simple irreducible subgroup of SPV or SOV. And we find that there are 2 main obstructions for H having finitely many orbits on a variety of totally singular K spaces. And they're easy to point out. So in the first case, it could happen that H is just too small. So if the dimension of H is not even the dimension of the variety you're acting on, we cannot hope H to have finitely many orbits. And the other issue could be if V has a large zero space. So let me tell you what this is about. So a zero space, call it here V0, is a fixed space of a maximal torus. So we have a nice maximal torus, keep it fixed. Look at this fixed space V0. And then if W is the Wagner group of H. So the normalizer of the torus will be by the torus. What do we have? We have that two elements in the zero space are in the same H orbit if and only if they are in the same W orbit. Okay, why is this useful? We have W, which is a finite group, and so the action in the zero space is controlled by this finite group. So whenever we have infinitely many of the objects we're acting on sitting inside the zero space, we know that H cannot have finitely many orbits on the whole variety. For example, if the dimension of the zero is at least 3, there are always infinitely many singular one spaces, and so H in general is going to have infinitely many orbits on the variety of singular one spaces. So using these two conditions, we're able to obtain a list of candidates. So if we're able to reduce the cases that we need to look at to the following table. It's a start, it's a finite table of things. There are many things. So once you achieve this reduction, all you need to do is go through every single one of these and determine whether you have finitely many orbits or not. We're gonna see a couple of examples. One thing to note maybe is that most of these cases have k equals 1 and k equals 2, though there are some femmes out there as before, which always it's a bit more complicated. But okay, and the reason for that is that overall the variety is going to be bigger and bigger as your the dimension of the subspaces grows larger. So it gets more and more difficult for H to have satisfy the dimension condition. That's why you sort of stop at the low K's. Okay, so let me give you the first result for k equals 1. So here we are looking at action on singular one spaces. So we have H being a simple reducible subgroup of SOV. Why don't we care about SPV? Because the action is on singular one spaces, but in SPV, every single one space is singular. So we wanted to have finitely many orbits on one spaces, on singular one spaces. Then either it was already a finite orbit module, okay, it had finitely many orbits on all one spaces, or it's one of the following. So similar type of result as the Group et al. Okay, again, the very first line is the only case where the stabilizer of a dense orbit. I should mention that since we have finitely many orbits, we have a dense orbit. So here I'm giving you a stabilizer of a dense orbit, also called generic stabilizer. And yeah, we're going to see some examples. But you see here a nice selection of modules, where the largest one, for example, is the spin module for B6, which has dimension 64. Okay, let's dive in the very first example. So we have, so let me go back. We have a 5-dimensional module for A1. We need, of course, the characteristic not to be 2 or 3. So what do? We want to choose a particular algebraically closed field K here, and you're allowed to do that. The answer does not change. So we take the algebraic closure of FP, and we want to pick a specific isogeny type for H. Here, let's have H being PGL2K. So this is a group of type A1. Then you start with a 2-dimensional vector space equipped with an alternating bilinear form. So here I use a basis E and F. So the form is 0 on E, 0 on F, 1 on E, comma F, minus 1 on F, comma E. And then we take the 4th symmetric power of W. So think of taking tensor product 4 times and then picking out the symmetrized tensors. So let's see some of them. So at this point, you can view this V as a reducible H module with highest weight 4 lambda 1. So this is a 5-dimensional irreducible module for A1. And it has we can do some considerations here. So the dimension of A1 is 3, and the dimension of the variety of all one spaces, as I said, just subtract 1 from the dimension of the module, that's 4. So this could not have been a finite orbit module. On the other hand, the dimension of the variety of singular one spaces is 3, because you subtract 1 more, which is the dimension of A1, so it does have a chance of being a finite singular orbit module. It's an orthogonal module. I can give you the symmetric bilinear form that's fixed by H. So you can just inherit this from the 4th tensor power, just taking the individual forms and multiplying them together. And because of these dimension considerations, a point in a dense H orbit must have a finite stabilizer. Okay? The dimension of the right is 3, the dimension of the group is 3, so we need a finite stabilizer. Okay, so what is the strategy? The strategy is to find orbits and then show that these are all the orbits. 2 orbits on singular one spaces are easy to find. For example, this is one of these symmetrized tensors I was talking about. This has stabilizer, which is the Borel, so parabolic, as you want to call it. Another singular one space. This is another symmetrized tensor. This has stabilizer, which is the rank 1 torus. Okay, these are nice connected stabilizers. Now for the dense orbit. So here you first start with an alternating group on 4 points. So this exists. You can and then use some character theory to show that it fixes, well, it fixes 2 one spaces, but it's acting non-trivially, so they must be singular one spaces. Again, this is not difficult. And in fact, you can show that this is the full stabilizer. You just look at the subgroup structure of PGL to Q, you see what the possible overgroups of alt4 are, and you observe that they cannot possibly fix these one spaces. Okay, so it's nice. We have found our stabilizer of the dense orbit, but who tells us that these are all the orbits? There might be other orbits that we haven't found. So the strategy here is to use a counting argument over finite fields. So this is a setup that occurs again and again. What do? We take Q to be a power of our characteristic P. Sigma is the standard for Benioff morphism, so it's acting on all our structures, so it's acting on K by raising to a QF power. It's also acting on our A1. You can think of it as sending a root element. You just raise the power of T inside by Q. And it's also acting on our vector space. If you fix a basis, then you can just act on the coefficients. Okay, then we take fixed points. So the A1 is going to give us a PGL to Q. And okay, for those of you who know, seen Max Steinberg before, this gives us a way of understanding how, when going to finite fields, the orbits behave. So they're going to split or not split depending on the connectedness of the stabilizer. So in particular, the first 2 orbits have connected stabilizers. So in our finite fields case, we have stabilizers of size Q times Q minus 1. This is the Borel. For size Q minus 1, this is your torus. So that's a nice case. More involved is understanding how this alternating group on 4 points splits. This is going to depend on the congruence class of Q mod 3. But overall, what you find is that so it either splits in 4 orbits or 2 orbits. But of course, in both cases, if you add up the sizes of these orbits, so 1 over 3 plus 1 over 3 plus 1 over 4 plus 1 over 12 is the same as 1 over 2 plus 1 over 2, which is 1. So overall, they add up, these orbits, to the size of PGL to Q. So then what do? You just add up the orbits that you found. So you divide by the sizes of the stabilizer, sizes of the second stabilizer, and these orbits coming from all four. You get 1 plus q squared plus q cubed, which you can check is precisely the number of singular one spaces in your module. And so you know that these orbits that you found were actually all the orbits. So let me give you the result now for k equals 2. Same setup, we want finitely many orbits on totally singular two spaces in this case. And the possibilities are as follows. Again, a nice finite list of cases. And we actually prove a stronger result. So we show that in these two cases, so k equals 1 or k equals 2, the property of having finitely many orbits is actually equivalent to having a dense orbit. This is a nice result that doesn't have to be true in general. In fact, for the case that was dealt by Grounding et al., they showed that this was only true for one spaces. Here we're also getting two spaces. So one direction is obvious, of course, if we have finitely many orbits, we have a dense orbit. But the other direction is not true in general. In our setting, very interesting, we find that there's only one exception. Okay, I haven't quite completed the classification yet, but I'm pretty certain about this. So this is the 14-dimensional module for C3, and we're looking at the action on totally singular 7 spaces. Very interesting case. Turns out that the generic stabilizer is finite, so there is a dense orbit, and it's actually a Frobenius group F7. But if you keep looking, there are infinitely many other orbits. So dense orbit, but infinitely many orbits. Let me quickly run through the example for k equals 2. So this is coming from the algebra for A2. Get the Chevalier basis from the Lie algebra. Then, because the characteristic P is assumed to be 3, there is a fixed vector, quotient out by that to get our 7-dimensional irreducible module. It's quadratic, we have a quadratic form. We already know the orbits on singular vectors, there's only 2 of them. So I can give you the representatives with the stabilizers. And then we play the same game. So we determine stabilizers of a certain list of totally singular 2 spaces. And again, here we're lucky, the stabilizers are connected. So when we do the same trick, going to finite fields, it's easy to understand. I mean, this just gives you one orbit in every case. So for example, we're going to have a stabilizer of size q in the first case because of the u1. And so again, play same game, you add up the orbits, you're happy because you had actually found all of the orbits. And let me conclude with showing you a case where we have no dense orbit. Because for now, I've only shown you how finite list of cases, you add up everything, you are happy because you found all the orbits. But sometimes the way to show that you have infinitely many orbits is to show that you have no dense orbit. So here we have the minimal module for E7, and this time the embedding is in SOV or in SPV depending on the characteristics. So H fixes a symplectic form if P is not 2, and otherwise it's an orthogonal form. So in the first case, it's easy to see that we have no dense orbit. So there's a nice characterization of generic stabilizers for the action on subspaces, recently completed by Grounding and Lotter. And what they found is that H acts on the variety of all 2 spaces with a stabilizer that has a connected component of type D4. So this is a 28-dimensional stabilizer. And since it's generic, it gives you a lower bound for the dimension of any stabilizer. And so you just look at what is dimensional variety, and you quickly see that it is not possible to have a dense orbit in this situation. However, when P is 2, it could still have, you would need precisely a 28-dimensional stabilizer to have a dense orbit, But what I managed to do was show that actually the lower bound is a bit bigger, and you need 29, the lower bound for the dimension of any stabilizer is 29. So again, by dimensional considerations, you conclude that there cannot be a dense orbit. And that's it. Thank you very much.